All right, so in our next example, notice now here it says determine whether or not the vector field is conservative. If it is conservative, find a function f such that f equals del f. Well, before when we had a function vector field, that had three variables, it had to tell us that it was conservative, or it had to tell us that f equals del f, which indicated that it was conservative. In this case, it's actually wanting us to determine that. Well, now we actually have the way to do it. So don't forget that if this is the case, if we want to find out if this vector field is conservative, now all we need to do is check the curl. If the curl equals 0, 0, 0, which is what we're going to find out, then it will be a conservative vector field. And then if that's the case, we can actually use the fundamental theorem of line integrals to be able to find out the original f function here. So let's go ahead and check the curl. So the curl of this thing, I, j, k, d dx, d dy, d dz, and then the x part is going to be 2xy. The y part is x squared plus 2yz, and then y squared is the k component. Okay, so there we go. Let's go ahead and check this thing out and see if it works. All right, eliminating the I row and column, I am going to do d dy of y squared, that is 2y, minus d dz of x squared plus 2yz, which is 2y. So far, so good. Then the middle part, we'll have to change the sign. It is going to be d dx of y squared. Well, that's 0. Minus d dz of 2xy. Well, that's also 0. So again, we get negative 0. Awesome. And then the k part, eliminating the k row and column, I am going to get d dx of x squared plus 2yz, that's 2x, minus d dy of 2xy, which is also 2x. Perfect. So we do indeed get 0, 0, 0. That is our curl of f, which indicates that this is conservative. And since it is conservative, now we can actually use the fundamental theorem of line integrals to be able to figure out the original f function. Just remember which piece is which. Now we do have all three of them here, so we got to go through a little bit of a process, but that's fine. So let's just label these. I'll keep it in red for now. This right here is our f sub x, this is our f sub y, this is our f sub z. All right, so let's start off with the fact that we know fx is 2xy, which means if I were to take the antiderivative of that with respect to x only, that's going to give us, what is that, x squared over 2. So x squared y plus some function of y and z. So we'll call that g of yz. Okay, and then we also have to check, not check, but we need to figure out our f sub y part. F sub y is x squared plus 2yz, and that comes from the original gradient. Now, taking and finding fy from the f function that we found in blue, our fy, now our derivative with respect to y from the one we found in blue, is going to be, what is that, x squared plus g sub y of yz. And since these two things in green have to equal each other, that means these two pieces must equal each other. So g sub y of yz equals 2yz, which means taking the antiderivative, again, with only with respect to y now, so g of yz is going to be y squared z plus some function of z, h of z. Okay, now we'll bring, let's go to red for this one. Now we'll bring the z component into this so we can find the h of z. If I go from, okay, what I first have to do is I have to plug what we just found back in for g sub y from here. So we're going to get x squared y plus the g of yz is y squared z plus hz. Now if we were to find f sub z, taking the derivative of this thing with respect to z only, well, that's just going to give us y squared plus h prime of z. But f sub z from the top was just y squared. And since this is just y squared, f sub z from the top, from what we found is y squared plus h prime of z, that indicates that h prime of z must be equal to 0, meaning that the antiderivative h of z is just some constant k. So ultimately, our final result here, I don't want to go with yellow because that won't show up very well. Let's do purple. Our final result here is that f, the original function that this thing came from, is x squared y plus y squared z plus k. And we're not being asked to find the line integral or anything, so I don't have to worry about plugging anything in. All right, and the last topic is divergence. If you thought that defining the curl was easy, and it really is, finding the divergence is even easier. The divergence is defined to be the dot product of the gradient and our vector field f. So it's called div of f, and it is defined to be the partial with respect to x, partial with respect to y, partial with respect to z, dotted with p, q, r. Well, of course, that's just going to be dp dx, plus dq dy plus dr dz. That is your divergence. So it is literally del dotted with f. So we're going to go ahead and take that, and we're going to go back up to the top and finish that one off. All right, so back to example 1 here. Now we have enough information to finish off the divergence. So we're going to answer part B. The divergence of f, again, was defined to be the dot product of ddx, ddy, ddz, dotted with 1 x plus yz. That is supposed to be a yz. Sorry about that. Try that again. X. True. I'm still on eraser. X plus yz. And then xy minus root z. So let's see. The first part, derivative with respect to x, 0. The derivative of the second part with respect to y is z. The derivative of the last part with respect to z is minus 1/2, so 1/2 z to the negative 1/2. Or, what we get out of this is z minus 1/2 root z. That is the divergence. Again, very, very simple to do. Nothing really challenging. Now let's talk about what all this stuff actually means.